Hello, welcome to another module in this massive open online course on the principles of CDMA, MIMO, OFDM wireless communication systems. In the previous module, we had seen how the SVD or the singular value decomposition can be employed to basically convert the MIMO or the multiple input multiple wireless channel into T parallel channels between the transmitter and receiver. We also said that this is basically the example of spatial multiplexing, that is employing the space dimension to multiplex multiple streams of information between the transmitter and receiver. Therefore, this results in a T-fold increase in the information rate or the rate of data transmission between the transmitter and receiver in a MIMO wireless system, okay. And that is how MIMO leads to higher data rates in 3G and 4G and of course subsequent generations of wireless communication systems. So today let us look at the maximum possible data rate or the capacity of a MIMO wireless communication system. So let us look at how to characterize this capacity of a MIMO wireless communication system. So what we are going to look at today is the capacity or the Shannon capacity, as is also known, of the Shannon capacity of a MIMO let us look at the Shannon capacity of a MIMO wireless system. We said in a MIMO wireless system I have y tilde I equals sigma I x tilde I plus w tilde I, where w tilde I is the Gaussian noise of variance sigma square, sigma I is the gain of the ith channel, x tilde I is the transmitted symbol. Let us have the power in the transmitted symbol, let us have magnitude x tilde I square equals Pi, that is Pi equals power of ith Pi equals the power of the ith transmitted symbol. Therefore, now you can see that this is the signal part and this is the noise part, and therefore, the signal to noise power ratio or what we call the SNR is equal to sigma I square Pi divided by sigma square. So, therefore, what we have is that for the ith channel SNR I equals sigma I square P sigma I square Pi divided by sigma square, alright. So, the SNR of the ith channel, that is we have T parallel channels between the transmitter and the receiver. The SNR of the ith channel, which we are denoting by SNR I, is given as sigma I square, where sigma is the gain of the ith channel, times Pi divided by sigma square, where Pi is the transmit power of the ith channel. And we know from the formula for the Shannon capacity that the Shannon capacity is given as log to the base 2 1 plus the SNR. Therefore, the Shannon capacity of this channel, the Shannon rate, let us call it the Shannon rate of this channel equals log 2 of 1 plus sigma I square Pi divided by sigma square. Remember, we have how many such channels? We have T such channels. We have I equals 1, 2, T. We have T such channels. Therefore, the sum rate equals summation I equals 1 to T log 2 1 plus SNR I or in other words the sum rate equals summation I equals 1 to t log 2 1 plus sigma I square pi divided by sigma square. This is the sum rate of the MIMO channel. So, what we are saying is the following thing, we are saying that the SNR of the ith channel is sigma I square times pi divided by sigma square, this is SNR I. The rate, the Shannon rate of this channel is log to the base 2 1 plus SNR I, which is therefore log to the base 2 1 plus sigma I square pi divided by sigma square. And therefore, how many such channels do we have? We have t such channels, where t is the number of transmit antennas. Therefore, the total rate that is possible in this MIMO system is the sum of the rates across these t channels, that is summation I equals 1 to t log to the base 2 1 plus sigma I square pi divided by sigma square. This is the sum rate. This is the sum of the rate, sum of the rates. The sum rate is naturally nothing but sum of the rates across the t parallel channels. Now, let us say, let us also assume that we have a total transmit power of P, which means the total power, that is the sum power summation I equals 1 to t pi is less than or equal to P, where P is the transmit let us assume that we have a total transmit power of P, which means the transmit powers P1, P2 so on up to Pt, these are the transmit powers of the T substreams or the sub channels. The total transmit power is less than or equal to P, which means P1 plus P2 up to Pt summation must be less than or equal to P, that is summation I equal to 1 to T Pi is less than or equal to P. And therefore, what is the capacity? The capacity is nothing but the maximum sum rate of the MIMO system subject to this total power constraint. So, therefore, what is the capacity of the MIMO channel? Capacity of the MIMO channel equals maximum of I equals 1 to t, maximum of I equals 1 to t log to the base 2 1 plus sigma I square pi divided by sigma I square pi divided by sigma square, subject to the constraint that the total transmit power summation I equals 1 to t pi is less than or equal to P. So, what we are saying is very simple. We are saying that the capacity of the MIMO wireless system, that is the maximum capacity, is the maximum possible sum rate, which is summation I equal to 1 to t log to the base 2 1 plus sigma I square pi divided by sigma square, subject to the constraint that the total transmit power, that is summation I equal to 1 to t pi is less than or equal to P, or we can even say the total power has to be equal to P, that is the total transmit power is equal to P. This is also known as a constrained optimization problem. This is known as a constrained optimization problem, and therefore, the way we are going to solve it, this constrained optimization problem, is by using the principle of Lagrange by using the principle of Lagrange multiplier. The way we do it is we form the objective function, which is basically summation I equals 1 to t log to the base 2 1 plus sigma I square pi divided by sigma square plus lambda, which is the Lagrange multiplier, times p minus summation I equals 1 to t of I equals 1 to t of pi. So, this is my objective function, where lambda, this is termed as the Lagrange lambda is termed as the Lagrange multiplier. So, we are forming the Lagrangian for this convex optimization, for this optimization problem, which is basically the original objective function plus lambda times the constraint, which is the total power constraint. Now, what we are going to do is we are going to differentiate this objective function with respect to each of the powers, because the optimization variables are the powers, that is p1, p2 up to pt. We are going to differentiate this with respect to each power, in particular with respect to the power pi, and set it equal to 0. So, what we can now do is we can differentiate this with respect to the power. So, differentiate this with respect to the power dou by dou pi. Now, once you differentiate this with respect to the power, you can see that I have derivative of the log is 1 plus the derivative of log of x is 1 over x. So, 1 over 1 plus sigma I square pi divided by sigma square times the derivative of sigma I square pi over sigma square with respect to pi, which is basically sigma I square pi over sigma square plus lambda times derivative of p with respect to pi is 0 minus, out of this summation only derivative of pi with respect to pi will survive, minus lambda times basically minus 1, the derivative of this pi with respect to pi is 1. So, minus 1 is equal to 0 is equal to 0. So, what I am going to have here is basically this implies that sigma I square pi over sigma square divided by 1 plus sigma I square pi divided by sigma sorry, there is no pi in the numerator, because we are differentiating with respect to pi. So, I have sigma I square divided by sigma I square divided by sigma I square divided by sigma square by 1 divided by 1 plus sigma I square pi divided by sigma square is equal to lambda. Therefore, let me rewrite this again. I have sigma I square divided by sigma square divided by 1 plus sigma I square pi divided by sigma square is equal to lambda, which basically I can now simplify as 1 over lambda equals pi, which basically I can simplify as 1 over lambda equals pi plus sigma square divided by sigma I square, which implies pi is equal to 1 over lambda minus sigma square minus sigma I square, and therefore, now remember the power has to always be greater than or equal to 0. Therefore, I am simply going to set this as pi is equal to 1 over lambda minus sigma square by sigma I square plus, which basically simply stands for the fact that pi is equal to 1 over lambda minus sigma square by sigma I square if 1 over lambda minus sigma square by sigma I square greater than or equal to 0 and equal to 0 otherwise. So, what we are saying is that the power Pi which maximizes the sum rate, or the power Pi which achieves the capacity of this MIMO wireless communication system, is given as Pi equals 1 over lambda minus sigma square divided by sigma I square whole superscript the plus, which basically says that is equal to 1 over the Pi is equal to 1 over lambda minus sigma square divided by sigma I square if 1 over lambda minus sigma square divided by sigma I square is greater than or equal to 0, and it is Pi is equal to 0 otherwise, that is the power Pi is equal to 0 if 1 over lambda minus sigma square divided by sigma I square is basically less than 0. Okay. So, what we have therefore now is that now we still have to find this lambda Lagrange multiplier lambda which is the Lagrange multiplier which is a Lagrange multiplier, this can be found from summation I equal to 1 to t Pi is equal to p, which basically implies that summation I equals 1 to t 1 over lambda minus sigma square divided by sigma I square is equal to p. So, solving this equation, yields lambda which is the Lagrange multiplier, and therefore, once you solve for lambda you can substitute in this back in this expression to get the power Pi of the ith channel for to achieve the maximum sum rate, which is also the capacity of the MIMO wireless system. This optimal power allocation is termed as the water filling algorithm. This optimal algorithm to achieve the capacity or maximum sum rate of the MIMO system is termed as the water filling algorithm. This is termed as the water filling algorithm. This is termed as the water filling algorithm. So, what we have seen is basically the power allocation Pi to maximize the sum rate, or which achieves the capacity of the wireless communication system, is basically Pi equals 1 over lambda minus sigma square divided by sigma I square superscript the plus sign, correct. And this power allocation algorithm, which basically leads to the maximization of sum rate, or basically which achieves the capacity or the maximum rate at which information can be transmitted, or which information symbols, information bits can be transmitted between the transmitter and receiver in the MIMO wireless communication system. This algorithm of power allocation, or this optimal power allocation scheme for the MIMO wireless system, is termed as the water filling algorithm. And this is a very key key scheme or a very key algorithm that helps maximize the data rate, helps increase the rate at which information can be transmitted in MIMO wireless systems. So, what we have seen in this module and some of the in the past module is how the SVD can be employed for spatial multiplexing to convert the MIMO wireless channel into T parallel channels, how the power can be allocated optimally amongst these T parallel channels to achieve the MIMO capacity or the maximum sum rate for MIMO wireless transmission. So, we will conclude our discussion here and look at other aspects of wireless communication systems in the subsequent modules. Thank you very much.